In this second video for Homework Packet 2.2, what we're going to be looking at is something called function notation. What is it, why we use it, and how to use it. So what is function notation and how do we use it? Okay. I've got three equations here. I call them equations because they have equal signs in them. All of them are y equals something. What we're going to do with function notation is we're going to replace the y value. The y value is going to go away in favor of a different notation. It's still going to act like the y value does as one of the variables, but it's going to be written differently. What we're going to do is we're going to rewrite the y value as f of x. So this equation will be rewritten as f of x equals 4x minus 8. So f of x equals 4x minus 8 is y equals 4x minus 8 written in function notation. This piece right here again is read as f of x. I can't stress enough, this is not f times x, this is f of x. Now you'll notice that realistically the f is just a label. There's nothing mystical or magical about it. It's just the label, kind of like y. Why do we use y? Just because we use y. We could have used p, we could have used r. All it is a label for a variable. Same with this f here. It's just a label for the variable y. But in function notation, it doesn't just list a label for the variable y, but it also lists what y is dependent upon. It's dependent upon x. Notice that that's the variable over here that you would plug something into in order to solve for y. So f, the function f, is dependent upon x. So how could I rewrite this second one right here in function notation? Again, I don't have to use f. I can use any label I want. Maybe for this one I'll use g of, but I'm not going to do g of x because y is not dependent upon x. Y is dependent upon t. So for function notation, this is going to be g of t because my y is dependent upon whatever I plug in for t. So this is going to be g of t equals t minus 4 all over t squared plus 2. Okay. This last one, maybe we could label this one as h. H of, we're back to an x here as our independent variable. So we're going to do h of x is equal to 3 times the log base 4 of 2x minus 9. Okay, so again, I replaced my y value with this function notation piece, h of x. The h is just a label for the function, and the x is the variable that's in the function on the other side of the equal sign. So h of x. Question now is, why in the world do we use function notation? Well, really there's two reasons. There's two reasons that we use function notation. The first reason is it allows us to account for several equations at the same time. You see up here I have listed 1, 2, 3 different equations. In original form, how would I have had to describe which equation I wanted to use? I would have had to read the whole equation out. I would have had to say, I want to use y equals t minus 4 over t squared plus 2. Well, in function notation, what do I have to say now? All I have to do is say, use the g function, because that's the function labeled g. Every function now has a unique label on it, in our case f, g, or h, rather than all of the functions just being a y equals. So it allows me to account for several equations at the same time. Okay? It also allows me to communicate what I want to do with the equations much more efficiently. And to illustrate that, what I want to do is I want to look at the next slide to show you how it allows you to communicate more efficiently. So I've got the same three functions here that we were working with, f of x, g of t, and h of x. Now look what I have right here. I have find f of 6. So here's why it allows me to communicate much more efficiently. If I say find f of 6, what does that mean? What function am I going to use? I'm going to use the function labeled f. There's distinction between them based on how I labeled each function. So when I say the f function, I know exactly which function I'm supposed to use. And it says f of 6, which means what am I going to plug in for x? I'm going to plug 6 in for x. So f of 6 simply equals 4 times 6 minus 8, because I used the f function and plugged 6 in for x. So f of 6 is equal to, let's see, 4 times 6 is 24, and then minus 8. So f of 6 is equal to 16. 24 minus 8 is 16. Now, this is where you stop. This is not f times 6. It is not f times 6. So if you at this point were to go divide by 6 to get f all by itself, you would be wrong. It is not f times 6, it is f of 6. What it's communicating is, how did I get this 16? I got that 16 by plugging 6 in to the f function. That's function notation, and that's what function notation allows us to do. It allows us to very accurately define which equation I'm using and what I'm plugging into it, and then it communicates how I got the solution that I got. How did I get the 16 again? By plugging 6 in for f. So when I come over here to h of 9, I already know what equation I'm supposed to use. I'm supposed to use the h equation. And what am I supposed to plug in for x? I'm supposed to plug in 9 for x. So h of 9 simply equals this right here with 9 plugged in for x. That's 3 times the log base 4 of 2 times 9 minus 9. So h of 9 is equal to 3 times the log base 4 of 18 minus 9. So in my calculator, I am going to do the log base 4 of 18. So log base 4 of 18. I'm going to take that answer. Now, real quick, why did I not subtract 9 from the 18? Well, because it wasn't in parentheses. All right? So only the 18 is a part of the log. Minus 9 is at the end. So I did log base 4 of 18 in my calculator, multiply that by 3, and then subtract 9. And I'm getting that h of 9 is equal to negative 2.75. So what is h of 9? It's negative 2.75. Where did the negative 2.75 come from? It came from plugging 9 in to the h function. So we can look at that one final time by maybe considering this one, g of 7. Well, g of 7 is equal to plugging 7 in for t of my g function. I know exactly which function I'm supposed to use and exactly what I'm supposed to plug in for t. So that becomes 7 minus 4 all over 7 squared plus 2. So that's g of 7 is equal to 7 minus 4 is 3. 7 squared, so 7 times 7 is 49, plus 2 is 51. So g of 7 is equal to 3 over 51. Which, interestingly enough, reduces to 1 over 17. 1 over 17. So g of 7 equals 1 over 17. Where did the 1 over 17 come from? It came from plugging 7 into my g function. Okay, so function notation allows us to label different functions and easily reference them and communicate exactly where I'm evaluating those functions at.